Okay, everyone, good morning. It's 9 o'clock. We'll go ahead and get started. Does anybody have any questions over anything that we've covered up to this point? Partial fraction decomposition or circles?
Uh,
Homework?
yes, sir. I have one question on the homework. I think it was like the fifth question where you put it in like right and stuff, but the computer wanted a different like form of the answer.
Mhm.
So on like our tests and stuff, if we put it in like the form that you put it in, will that still be correct or?
Yeah, that's fine because remember, you'll be taking your test paper and pencil. So we won't have the issue of the computer, kicking back an answer. So yeah, don't worry about that.
Yeah.
Could you go back and look at that one? I'm sure a lot of people got it wrong. It's just the order in which you type it came up as incorrect, but I had the same problem. I think it was problem number 5 of the second homework.
It was 4 or 5, yeah.
Yeah, let me bring it up here.
Because I put it in 2 ways, and I'm pretty sure one of the 2 were correct.
Okay. And I don't know if you all remember, but I told you I haven't taught pre-cal in a long time. So this is actually the first time I'm using this system in quite a while. So I'm kind of learning still here. Okay, was it this one, question 4? Yeah. So let's see, was this the one? Yeah, okay, so the correct answer. Yeah, so the only thing that was incorrect in my answers, I did not simplify the square root of 8. So what they wanted was, so you can see everything else matches perfectly. They wanted me to rewrite the square root of 8 as 2 root 2. Is that what you're referring to, or?
Does it matter if you put the plus or minus first?
I don't think it shouldn't.
Because,
it shouldn't matter, like if you did plus here and then minus.
Yeah,
No, it
I did
doesn't
that
matter.
the first time
Really?
and I got it wrong.
Really? Okay, yeah.
Yeah.
I mean, hold on.
The
Does
I've
it
switched
say
up
in
the
the
order before and it
instruction?
never counts it wrong for me.
It didn't count it wrong for you, Maddie?
No.
Okay.
Oh.
Yeah, I mean, the system should know that it's going to look at each of the answers separately, and it should take it in any order. But yeah, I would not worry about this. I'm going to go back and just give everyone that got it wrong credit. So there's no big issues here. This is one of the things, using technology to put math answers in is kind of frustrating, and I don't want you all getting frustrated with the computer. As long as you understand what you're doing. I know it's frustrating because you want to know if you got it right, but it will show you the answer at some point, and you can compare it and say, okay, yeah, I had it.
Also, if you go to the top tab, it says question help, and you can click help me solve this or view an example, and it'll show you kind of how to do it if you don't know what you're doing.
Okay, so if you say view an example, then it'll show you the format that they're looking for the answers. Right.
Yeah, their format can be kind of drawn out though if you don't.
Yeah.
But that question 6 was dirty. I mean, it was good, but it got me. I didn't realize it was the diameter of the circle, not the radius. It got me good.
Yeah, on 6. Okay.
Yeah, I was like, I kept reworking it. I was like, man, I'm getting this right. I don't know, but then I didn't realize it was the diameter.
Yeah.
I didn't read the right.
Okay. Good. Was there anything else? Okay. Well, here's where we are today. We're on track so far. We're supposed to cover 7.1. So we're starting chapter 7, and I mean, we don't have our first exam till March, so we're still quite a way away from our first exam. But this is where the majority of your test is going to be this, and it's all going to be interconnected and related. Everything, I think I told you this last time, everything else that we had done is kind of like, okay, this is stuff you'll see again, but now chapter 7, every section is going to kind of build off the previous. All right, so today is just a ton of definitions. There's a bunch of things we have to get out of the way. I listed out all the different definitions and concepts that we have to cover today. And a lot of you have seen this before, whether it be in high school or even sometimes in like middle school, you'll talk about some of the basic geometry, angles and things like that. So, you know, I know that it's going to seem maybe for some of you like I know this already, but just bear with me because we really need to make sure that we have this foundation in place, because when I start using this terminology later, if you're like, well, I don't remember what a quadrantal is, then it's going to be an issue perhaps. Okay, so here we go. We're going to start with the idea, you know, we're talking about angles and degree of measure. So the first, I'm going to be flipping back to this and just kind of crossing these out as we go. So the first concept that we're going to be talking about here is array. This is going to go kind of quick. So when you talk about, you know, what is array? This is a geometric object, and you know, we're familiar with a line. A line, right? A line is, you know, a collection of points, right, that all lie on this straight line, and you can imagine that that line goes in both directions forever. So I have to put arrows here because I in each direction forever, right? So that's a line. If we wanted to look at just the points on a line between 2 points, we call that a segment or a line segment. You can call it either one. I'm going to just call it line segment. So here you stop, right? Then you have the concept of array. An array is, again, the points on a line, but you stop at one point and you go the other direction forever. Okay, this is what array is. You know, it doesn't matter which way your array goes. Okay, you just have to have a stopping point and then the other direction forever. Okay, so that's array. We good? Okay, the next thing is what's called the vertex. So the vertex is when we're looking at array, okay, so when we're looking at array here, the vertex is this point right here. It's that end point. We call that the vertex of the ray. Okay. Now, the concept of an angle. Let's see, what is an angle, right? So an angle is what you get when you take two rays, okay? You start with two rays. And you connect the vertex, or vertices is what I should put, but I'll just put vertex here. You connect their two vertex points together. Whenever you do that, anytime you take two rays and you connect the vertex together, you'll have, let's see, I'm going to do one ray that's in green. Then I'll do another ray here that's in purple. Okay, anytime you take two rays and put them together like that, you create what's called an angle. And we're all familiar with angles, but what it is this right here. And it's very hard to describe what is that geometric shape between the two rays, right? Like, what is it? We call that an angle, right? I'm sure you've heard of degrees and things like that, but this is like, before we talk about degrees, what do we call that object between the two rays? It's called the angle. Do you understand, like, it's really hard to define what I'm talking about? Because I'm talking about like this space in between these two. But as you move further out, the space gets bigger, doesn't it?
So it's like the degree of separation between two connecting rays.
It's like how far separated they are, right? But the problem with that definition is that if you look like really close right here, they're not separated by much, are they? But if you go way further out, there's a bigger separation, right? So it's still
can't degrees be defined as a ratio?
Pardon?
Couldn't degrees be defined as a ratio then, and then it would be consistent?
A ratio of what though? Like what to what?
Length over height.
Well, these go forever though, right? Like you have to imagine this keeps going. So you can't really talk about a length there, right? We'll define it. All I'm trying to say is that the concept of an angle, we all know it. Like we all have talked about angles before, but when you really think about it, it's kind of hard to put your finger on exactly what you're talking about. Because you're saying like, it's a measurement of like this thing between these two rays. But again, as you move out, that kind of changes, right? It's a different size depending on where you are. Okay, so we're just gonna stick with this. Angle is somehow this sort of object that's between the two rays. All right. So we're doing a little wave, hand waving here, which means we're kind of giving up a little bit. Okay, initial side. So when you measure an angle, okay, I'm going to do initial and terminal side together here. When you measure an angle, I'm going to start a new one. Okay, so when you take an angle and you want to talk about this angle here, let me label it. Okay, I'm just going to put that there. When we talk about an angle, again, it's formed by two rays. We have to have what's called an initial side and a terminal side. And that's kind of up to you, or it might be stated within a problem. So in this case, I could make the purple one my initial side. So I could do this. Let me copy and paste this. So I kind of have two options here. I could say that this one is my initial side. And this one is my terminal side. Or I could reverse it, and I could have said that this is my initial side, and this one is my terminal. And that makes a big difference. It makes a big difference because when you're talking about an angle, you always start at the initial side and then go towards the terminal side. So in this particular case, the angle actually goes and starts on this side and ends here. So I'm put a little arrow like that. So we're measuring the angle we're measuring goes from here to here. Whereas on the one on the bottom, zoom out a little bit, the angle goes the other way, okay? So these two angles, the way I have it drawn right here, these two angles are not the same. Okay, they're not the same. Even though the two rays are the same, these two angles are not the same. So the convention is that if your little arc that I'm drawing here, if that thing is counterclockwise, then it's a positive angle. And if it's clockwise, so I'm going to say counterclockwise, opposite way of a clock, right? And then it is a negative angle if it is clockwise. So is everyone clear with the idea that even if you take these two rays, even if they're exactly the same rays like this, if you call this the initial side and this the terminal, you have a positive angle. But if you do it the other way, initial side, terminal side, you actually have a negative angle. Yes? So you have to know what the initial side is for you to be able to tell me whether or not you're dealing with a positive or a negative angle. Any questions? Sure. Okay, so let's see here. What's the next thing? I actually killed off a few things here. Positive angle, that's a counterclockwise angle. Negative angle, that is our clockwise. Now, what is standard position? This is very important to us. Standard position. So when you are sitting here getting ready to draw an angle, we all kind of have to agree on a convention that'll make it easier for us to communicate with one another. So imagine, I'm going to put what we're doing here, standard angle, or sorry, standard position. So when we've been dealing with two-dimensional space, do some grid paper here. When we've been dealing with graphs and things like in college algebra, we always drew the XY axes, right? So we always said, okay, this is the X and this is the Y, right? This is the positive direction of X. This is the positive direction of Y. So when we're talking about standard position, here's what it is. It's an angle where the initial side is a ray that starts at the origin. Okay, so I'll write this down in words in a second, but it's a ray that starts at the origin and goes out parallel to the x-axis. So it goes along the x-axis. So that's your initial side. Now, your terminal side can be anywhere you want it to be, all right? So let me just put another ray like this. I'll make it longer just to remind you these things go forever. Okay, so let's say that that's my terminal side. Now I have a trick question. You ready? I have a trick question. So let's see who's on their toes today. I guess we'll start out with, let's see, who did I not get through? I didn't talk to Brianna, I don't think, last time. Is Brianna here?
I'm here.
Hi, Brianna.
Hello.
How was your weekend?
It was busy. I had to work.
Yeah, we had family and I don't think I went to bed before 3 a.m. any day this weekend, so it was crazy.
Sounds about right.
Yeah. Okay, so here's a trick question, all right? Is the angle here positive or negative? And this is a trick question.
Based off of the notes that we just took, it would be positive.
Okay, what do y'all think? Seem reasonable?
Depends how you measure it.
Yeah, because
What do you mean?
I mean,
So you could start from the initial side, but you could go counterclockwise, or you could start from the initial side and go clockwise.
Yeah. So when I that was a totally loaded question to Brianna, because what Brianna did is what most of us are going to do is think that I'm talking about going from here to here, right? Which in that case, if that's the angle we're talking about, then I agree that that is a positive angle. However, you could have gone from the initial side clockwise all the way back to here. And now we're talking about a different angle, and that angle is negative. Do y'all see what I'm saying? So what I should have done is I should have asked Brianna, hey, Brianna, this angle right here, is that positive or negative? And then she would have been able to say, yeah, it's positive. You see what I'm saying? Is that confusing, or does that make sense to it?
is that why it's called standard position? Because it could be either or?
Well, it's standard position. The only thing that makes standard position is that the initial side starts at origin. I'm going to put starts at 0, 0, because that's the origin right there. And then goes along the x-axis in the positive direction. Okay, so standard position just means that whatever angle you're talking about, the initial side starts here and goes this direction, and then the terminal side can be anywhere, okay? But if we do that, right, if we draw all of our angles in standard position, then we will all get the same answers in terms of our angles. Like we'll all agree that this angle right here, the positive angle between these two, we will all agree on that measurement is the same, right? Or that angle measurement is consistent with all of us because of where we've placed our initial side.
So is this why we're allowed to determine what's the initial side and what's the terminal side for the sake of standard positioning? Or is that one of the reasonings why?
I'm not quite sure I understand.
So you said we're allowed to determine what side is the terminal side and what side is the initial side, correct?
In general, you can, given two rays, you put them together, you can always decide which side's initial and terminal.
Okay.
But if we all agree at least that the initial side's going to run along the x-axis right here, it's just going to make life very, very easy for all of us to be able to communicate with each other, because we will all at least be starting with our initial side here. If we don't do this, if we don't have some convention, then if I say, okay, you know, I want you to draw this certain angle, one person could come in here and say, oh, this is my initial side, this is my terminal side, and we're talking about the angle between them here. But then someone else could have drawn it like this. You see, excuse me. And even though these two angles are positive, and even though they are exactly the same, they're not positioned in the same place. So they look completely different, but they're not. So what we do is we bring this initial side, we bring that initial side, and we force you to draw it starting here and going this way. And then everyone's graphs, everyone's rays will come together and look the same. So it's just for consistency. That's why we call it standard, because it's kind of like the standard that we're going to use.
Yes, sir. Do you prefer doing a method? Do you prefer having terminal like always stay one side, or the initial stay one side, or do you just like, does it depend what problem?
I think the problem is going to dictate what is initial and terminal.
Okay.
But no matter what, we're going to be putting the initial on the x-axis pointed to the right. Okay, now, quadrants. Oop. So I think that it's pretty natural for us to consider that when you have two-dimensional space like this, right? If we are going to be measuring all of our angles using standard position like this, if we're going to be doing that, then it's natural to see that a flat sheet of paper is broken up into 4 different regions, right? We have 4 separate sections that the angle could kind of fall into. And so we call them quadrants, quad for 4. And we name them, okay? So we name the first quadrant, okay? Quadrant 1 is here. That's quadrant 1. Quadrant 2, I'm using like Roman numerals, is here. Quadrant 3 is here. Quadrant 4 is here. I'm using Roman numerals because that's what most textbooks use. Now, if you think about this, and you know, I always ask my calculus students, you know, why did we label it, you know, 1, 2, 3, 4? Why didn't we just go like 1 is here, 2 is here, 3 is here, 4 is here, like reading a book? The idea is that when you start talking about positive angles, right? Positive angles, you're always going to start over here, like that would be a positive angle. Agreed? That's some positive angle. But as that angle gets bigger, that ray is going to start moving, right? So now that's a bigger angle. And then if I move it more, it's going to wind up over here. That's a bigger angle, positive, right? And then a bigger angle, and then bigger, and then bigger, and then bigger, right? And so it seems natural that we would want as our angle gets bigger, to move through the quadrants in order, right? So we want to move through quadrant 1, then into quadrant 2, then into quadrant 3, then into quadrant 4. So that's why we label it this way, so that it follows the counterclockwise nature of a positive angle. So quadrant 1, quadrant 2, quadrant 3, quadrant 4, right? So 4 quadrants. Questions? All right, the next definition is a quadrantal. Okay, so what's a quadrantal? It's a weird word. I have trouble saying it. So a quadrantal is an angle, okay, where your terminal side falls on one of the axes. So here would be, if you had this angle, this ray, see this ray here? It's going straight up. That would be a quadrantal. Wow.
So anything that has a right angle?
Nope, not a right angle. Not a right angle. Any terminal side that lies on one of the axes. So that would
Okay, but
qualify.
if we start it, or it has an angle that's a multiple of 90, right? Because if we
Oh,
go off a
hold on,
standard
Joshua.
position,
Joshua, hold on for a second, because we haven't talked about what you're talking about. Right now you're talking about 90 degrees and right angles. We have to pretend that we have no idea what you're talking about right now.
okay.
Right? Because I haven't defined what a degree is yet. We want to look at this as a very general thing right now. Right now we have the idea of rays. From rays, we get the idea of an angle. From angles, we talk about initial terminal side. From that, we talk about positive and negative. Then we talk about, oh, it breaks up the plane into 4 pieces. And all I'm saying right now is that if your terminal side lies either on the y-axis here, the x-axis here, the y-axis here, or even if your terminal side brings you back here, okay, like all the way around and back, even if that happens, those 4 different angles that we're talking about are called quadrantals. Does that make sense? What we're trying to do is this, okay? Let me try and illustrate what we're getting. Why do we have to do this? Okay, if I give you an initial side here, and then I give you a ray, another terminal side here, I think everyone could say that that lies in the first quadrant. Does everyone agree that that angle is in the first quadrant? Okay,
Yes.
but if I give you this one, and I tell you that's the terminal side, what quadrant is that in? Well, it's not. It's not in the first quadrant, right? It's not in the second quadrant. So what quadrant is it in? Well, it's not in a quadrant. That's a quadrantal. Quadrantals don't lie in a quadrant. Does that make sense? So we just need a name. We need a name for those. Now, Joshua, later, when we talk about degrees, of course, we're going to say that this is a right angle and it's 90 degrees. And then this will be, 180 degrees and 270, but we're just not there yet. Any questions? Quadrantal?
Do we label the quadrantals like we do the quadrants, or are they just considered quadrantals?
Yeah, just remember that we can call them something. They actually don't come up very often, but I know that the book does use the language in some of the homework, I believe.
Oh, okay. So anytime we see them, just acknowledge them, but like we don't have to label them.
Yeah, I wouldn't label them.
Okay.
Okay, now we talk about a degree. Okay, so look, at some point in history, humans had to figure out a way to measure these angles, right? Just like when you think about a ruler, right? You have a standard ruler, and most rulers in the United States of America are going to have 1, 2, 3. It's going to be usually 12 inches, right? So this is 1 foot, and we break it up into 12 inches, right? And then how many pieces do we usually break up an inch into? Does anyone know what our breakup of an inch is? I mean, like a foot, we break it into 12 pieces.
And
But
then
each inch we break into usually how many?
10, right?
16.
Oh wait. It's
16.
Usually 16ths of an inch or even 32nds of an inch.
yeah.
It's man, we're all screwed up. Okay, like our measuring system is all messed up, and this is the imperial metric system that's passed on from Europe, from the kings and royalty. I mean, literally, they used to just, when they would say, "What's 1 foot?" It literally was whoever was the king at that time would put his foot out there and they'd measure it and they'd say, "That's a foot." Okay, and so it actually varied from generation to generation. But before that, they didn't have anything, like they didn't have rulers, right? So they needed a way to measure, like, how much land do you have? That much, right? You just point at it, that much. Well, you need a way of measuring it. So the standard was a foot, right? And then now we realize that that's not a very good system. At least we all agree upon what a foot is, and it doesn't change. But it's still a really bad system, just the way we break things up. The metric system is much better. but that's a conversation for another time. So at some point, what we needed to do was to decide, how are we going to measure these angles, right? How are we going to measure them? And so what was decided, and this is debated. Historically, it's debated who came up with this or where it exactly came from. But what was decided ultimately was that what we're going to do is we're going to take a circle. I put together a little animation here for you. What we're going to do is we're going to take a circle, and oh shoot, I heard noise in the other room. I forgot my daughter didn't go to school today, so I was like, what the heck? Someone's in my house. Okay, so we take a circle, and what we decided was that we would talk about angles. Do you see that each of these red lines forms a different angle, right? Each one of these by themselves is a different angle. We decided we would break up a full revolution all the way around into 360 equal angles. So if you go and look at each one of these tiny little angles, each one of those is 1 part out of 360. So we have a name for this. This angle, okay, it's really hard to see it in here, but that angle right there is called 1 with that symbol. That's 1 degree. I know most of you know this already. All right.
The circle is called a unit circle, right? Or is that something different?
Well, this happens to be a unit circle, but it doesn't have to be a unit circle for you to talk about degrees, no matter which size this circle is. So if I were to draw another circle like this in here, then each one of these would still be 1 degree, because you're still cutting up that full revolution into 360 equal pieces.
Okay. So every little marking's 1 degree.
Mm-hmm.
Okay.
Well, the space between each one of these is 1 degree. The measurement of that angle. See, again, we go back to, how do you define angle? It's weird. Okay, so there are 360 degrees in 1 full revolution. So that means, going all the way around, right? If I were to go all the way around, starting at the standard position, where's my pen? It's not drawing. Oh, I know what's going on. Okay. So if we start in standard position, right? And we go all the way around, okay? And stop there. So basically our initial side and our terminal side are in the same place, but we go all the way around, then that would be 360 degrees. Any questions? Again, I know a lot of you have seen this. So any questions on all the way around 360? Now, there is an argument that the reason they chose 360, there are 2 arguments that I've heard. Is one, it came from, I think, the Babylonians, who used a number system that had 60 digits in it. You know how our number system has 10 digits? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So our number system has 10 digits, right? I was actually talking to my daughter about this. You know what? Hold on a second. Hey, Matt. Where are you? I'm in the middle of class. You don't have to come on camera. Just come to the side. Right here. Okay, so my daughter's in here. So her name is Maddie. She's not going to come on camera because she just woke up. So we have 9 digits in our number system, right? So why do we have 10 digits in our number system? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 digits. So why do we have 10 digits in our number system?
Because it's based on you have 10 fingers.
Okay, good. That's good enough. Go wake up. Did y'all hear her? It's the fact that humans have 10 fingers, right? So if like we had 8 fingers, then we would have a number system that had 8 digits, because it's just natural, right? That's where it came from. The Babylonians, for some reason, used a number system that had 60 digits in it. And they're all symbols. They don't look like our numbers, but that's one argument, that it's because of the Babylonians, all right? The other argument is that 360 is what we call a highly composite number, which just means that there are a lot of numbers that can divide into 360. Like 2 goes into 360, 3 goes into 360, 4 goes into 360, 5 goes into 360, 6 goes into 360, right? There's a lot of numbers that divide into this. So, you know, the argument is that they chose a number that's highly composite. We don't care. 360 is what we got. That's what we all use. So we're going to stick with it. Okay. Get back to the notes here. She's going to be mad at me that I pulled her in here to do that. Okay. We have degree. So hopefully we understand what a degree is. 1 degree is 1 part of 360 out of a full revolution. And now we have 2 new things called right angle and straight angle. So a right angle, go back to my picture here. Okay, so if you take your initial side, right, standard position, and you take an angle that is formed where your terminal side lies straight up like this on the y-axis. So that is a quadrantal, right? But it's a specific one. Then the measurement of the positive angle between them, that's this angle right here, that measurement would be 90 degrees. And the reason, I hope, is obvious to you. If the whole way around is 360, and this is only 1/4 of the way, then if you just take 360 and divide that by 4, you will get 90 degrees. So this must be 90 degrees. And we normally label that not with a little arc like that. We usually use a little box like this. And that is what we use to represent the fact that it is a perfect, like it crosses at a perfect T, I guess you could say. Right? So that's 90 degrees. This is called a right angle. So a right angle, right, written in standard position like this, a right angle is also a quadrantal. Now, if we go and instead of doing 90 degrees, we do 180 degrees, that would put us over here, right? That's this ray. That's what we get when our angle does this. Starts at our initial side and comes over all the way across to here. Now, how many degrees is that?
180.
180, right? Because it's halfway around. So if you take 360 and you divide by 2, you get 180. So this will be 180 degrees.
Would that be an obtuse angle?
It is obtuse, but when we say acute and obtuse, a lot of times we're talking about triangles, the measurement of angles within a triangle.
Okay.
Here, so anything bigger than 90 is obtuse, okay? Anything less than 90 is acute. But on this picture, we call this just a straight angle. Just make sure I'm in the right, okay, yeah. So this is going to be a straight angle. And that's because it's straight, right? Like when you look at this ray and this ray together, it creates like this, almost like a straight line. So it's called a straight angle. Now we could go more, we could go another 90 degrees and that would point us straight down like this, right? Now that could be the angle that goes like this all the way to here. Now there's not a name for that one, okay? There's not a name. And the reason there's not a name is because if you look at that angle measured backwards, okay, this way instead, do you all agree that that would be negative 90 degrees? And that would form a right angle here, like this. So there's not a special name for 270. Sorry, I didn't put 270 here. This green one is 270. So if you go initial side, counterclockwise around to here to point straight down, that's 270 degrees. But if you look at it clockwise, it's negative 90. And it forms a right angle. No special name for it though, but you need to know 270 and negative 90. Any questions? if you wanted to, you could still call this a right angle.
For the is there a specific name for the 270 or no?
No, that's what I'm saying. There's not a name for it.
Just making sure.
Yep. All right, moving on. Right angle, straight angle. Okay. I'm really not a big fan of the next part, but we got to do it. Okay. We're going to talk about 1 minute and 1 second. Okay, so I'm going to go back to this thing that I put together here. So if you take this full revolution, we broke it up into 60 equal pieces, right? I'm sorry, 360 equal pieces. Each one of those is called 1 degree. Well, just like our ruler, you know how our ruler is broken up into 12 equal inches, but then sometimes that's not accurate enough, so we have to break each inch into 16 pieces or whatever it is. We need like a finer way of measuring. Well, we need a finer way of measuring this too. Maybe a degree is not small enough sometimes. So what we do is we take 1 degree. So do y'all see this here? This is kind of like we're zooming in and we're looking at this right here is 1 degree. Well, I should do it this way. Like that angle right there is 1 degree. What we do is we break that degree up into smaller pieces. And what we do is we break it into 60 pieces. And so here they are. It's going to be hard to see them, but do you see that there are 60 smaller angles in there? Each of those tiny little angles in there, each of those is called 1 with the little dash right there, and that stands for 1 second. Oh, sorry, minute. Oops, it's Monday. 1 minute. So in other words, there are 60 minutes in 1 degree. There are 60 minutes in 1 degree. And then we can take each of these tiny little guys right here, and we can break each one of those into 60 more pieces. Now I don't have an animation to show you. Okay.
So then it'd be like 3,600 seconds.
That's right. Now I'm going to write that down here in a moment, but imagine now, okay, imagine now this picture that we're looking at. Imagine that this picture is actually that this right here, imagine that that is not 1 degree, but imagine that that's 1 minute. We can take that 1 minute and break it up into 60 equal pieces. And each one of those equal pieces is 1 second. And we do 2 little dashes there. So that means that there are 60 seconds in 1 minute. Sorry, this is called a second. 1 second. Now, I think minutes and seconds make sense because we use that for time, right? 60 seconds in a minute, 60 minutes in an hour. Here, what we're saying is 60 seconds in a minute, 60 minutes in a degree. So that means, let me summarize all of this on a different page. So when it comes to minutes and seconds, we have this. There are 360 degrees in 1 revolution, right? 1 revolution. There are 60 minutes in 1 degree. There are 60 seconds in 1 minute. So I have a question. Someone already answered this. How many seconds are in 1 degree? So how many?
3,600.
In 1 degree. Yeah, so what we need is a way of actually doing this. Like how do you like mathematically do this? So how many seconds are in 1 degree? So what I could do is this. I could say 1 degree. I could say, all right, well, 1 degree is 60 minutes, right? And then here's the trickier part.
You could use a conversion ratio, right?
Yeah, so this would go back to college algebra or even before that. How we do conversions, unit conversions. So I would write 60, here's where we are, 60 minutes is where we are. And we're trying to get this to seconds. So we look at where we have a relationship between seconds and minutes, and that's here. This right here, we can use in 2 different ways. We can either write this as 1 minute over 60 seconds, or you can write it as 60 seconds over 1 minute. Okay, these are called conversion factors. And so if I want to take 60 minutes and I want to convert it to seconds, what I do is multiply it by one of these 2. And the one that you're going to choose is the one that would cancel the minutes out, which means I need the one that has minutes on the bottom, not minutes on the top. So I'm going to multiply this by 60 seconds over 1 minute. And what happens is the units, those minutes, kill each other off. And all you're left is 60 times 60, which is 3,600, what are we at, seconds. So there's 3,600 seconds in 1 minute. I'm sorry, in 1 degree. We're going to do more of these, okay? So don't freak out.
So always we want to make sure that they cancel out. So we use one of the 2.
Yes.
So whichever cancels it out is the one we use.
That you're going to multiply by, yes. And in fact, this one right here has 2 different ways that we could use it. We could go 60 minutes over 1 degree, or we could do 1 degree over 60 minutes. And we could actually do the same thing for this. We could say 1 revolution is 360 degrees, or we could say that 360 degrees is 1 revolution. We're about to do some examples, all right, so that we can get practice with this. I hate this topic, and I'll tell you why I hate it. Because in the real world, we don't usually use minutes and seconds and stuff. We really don't. But it's still part of our curriculum, so I'm doing it. But all right, let's do some practice here. So wait.
Isn't that how we measure like geographical coordinates, though, latitude and longitude?
Yeah, we do use it, but the thing is, like in mathematical computations, a lot of times we just convert that to a decimal. So it's like let me give you an example. If I write 12.5 feet, okay, 12.5 feet, that's 12 feet and then half a foot, right? But half a foot, right? Half foot, isn't that really 6 inches? Right? So I could have wrote it this way, 12 feet, 6 inches. Right, that's one way I could write 12.5 feet, 12.5 feet. I could write 12 feet, 6 inches. I'm saying that in the real world, we usually don't use that, we use this. And so with the angles, to say like 23 degrees, 4 minutes and 15 seconds, most of the time that's going to be like 23 point something degrees. We just keep it as degrees, but as a decimal. I hope that makes sense. Okay, I have to do another topic before we get into convert. Well, you know what? Let's do the conversion. I think it'll confuse you if I move on to radians now. Not confuse you, but it doesn't flow naturally. So I'm going to bring up the homework. Let's take everyone, why don't we take just like a 2-minute break. If you need to go do something, get a drink or something, just give me 2 minutes. I'm going to bring up the homework so we can take a look at it. Okay, let everyone get back in here. So these problems I took directly from the homework. So you may get this exact problem, you may get something similar. There's only 2 problems on the homework like this. So we just need to make sure we know how to do it. So the first question is for us to convert the angle to a decimal in degrees. So this is exactly what I was just talking about. If I were to tell you, hey, take 12 feet 6 inches and convert that to just feet as a decimal, then the way we would do it is we would say, okay, we know that this is 12 feet, right? So we know it's 12, but we want to know how much of a foot that is. So 6 inches is how many feet? So what we would do is we would take the 6 inches and we would multiply it by something that has feet and inches in it. And we know that there are 12. I'm just showing you this so you see what I'm about to do. There's 12 inches in 1 foot. So what I would do is multiply this by something that would cancel the inches out using this. And this leaves us with 2 different things we can do. Inches over 1 foot, or we could do 1 foot over 12 inches. I'm doing like a very crash course in conversions here. I'm going to choose this one because it has inches on the bottom. So I multiply by 1 foot over 12 inches, and the inches cancel. And so what I get is 6 across the top, 6 feet over 12. And 6 divided by 12 is 0.5 on, well, your calculator if you need that. So 0.5 feet. So what I would do is add that to this. So that gives me 12.5 feet. Okay, that was just real quick how we would do something like this with feet and inches, but I'm going to do it here for degrees and minutes and seconds. Okay, so if you didn't understand that, don't worry, let's just go through this. So I want this written in degrees as a decimal. So first thing we're going to note is we have 20 degrees plus, right, this is what this really means, 49 minutes plus 41 seconds. So if our final answer needs to be in degrees, every one of these needs to be converted to degrees. And what I had stated here in the previous note was that we can use these 2 if we ever want to go from minutes to seconds, and we can use these 2 if we want to go from degrees to minutes. So why don't we take these and just copy these over just so we can have them on the other page. I'll throw them down here. Get rid of that. Okay, so here we go. I want to try and get this to degrees and this to degrees. So let's start with the 49. I'm just going to do this like separate work down here. I have 49 minutes. Now, I want to go from minutes to degrees, so I'm going to be using these. And I want the minutes to cancel. So I'm going to use this one because it has minutes on the bottom. So I'm going to take this and multiply it by 1 degree over 60 minutes. And now the minutes are going to go away. So those minutes cancel. And I will have 49 degrees over 60. And so I get on my calculator now and I do 49 divided by 60. And unfortunately, I'm getting a repeating decimal. So this is approximately 0.81666, and it goes forever. Degrees. Are there any questions on that? What I did there?
If it's a repeating decimal, how far do you want to go to show it, or do you just want repeating?
It doesn't say here right now how far to round it. So we'll go to the computer and we'll put it in and we'll see what it tells us, okay?
Yes, sir.
Okay. So does everyone agree that I have converted the 49 minutes to degrees? Yes? Okay, the next thing to do is to try and get the 41 seconds into degrees. So we don't have well, yeah, let's just do it this way. We don't have a conversion down here that takes us straight from seconds to degrees. So the first thing I'm going to do is go from seconds to minutes. So I'm going to try and kill these off. Can someone tell me what I'm going to multiply by if I want to kill off the seconds? And
1 minute over 3,600 seconds.
1 minute. Oh, yes. I'm going to use this though. You're
What
using a conversion factor I don't have up here, so I didn't want to use that. I can do it that way too.
We would just do the 1/60 then, yeah.
Yeah, 1/60. Then these would cancel, right? But now I'm still in minutes, right? So I need minutes to go to degrees. So now I'm going to do this one next to that. 1 degree over 60 minutes. And now the minutes will cancel. So at the end of all this, you multiply straight across, you're gonna have 41 degrees over 60 times 60, which is 3,600. I heard someone say that. So we do this on our calculator. And I'm getting approximately 0.01138888. Looks like it's repeating. So coming back up here to the original question, what we're saying is that this is 20 degrees plus what we got here, which is 0.81666 repeating degrees, plus what we got here, which is 0.011388 repeating degrees. And so we're going to add those up. Because they're repeating, I'm only going to go out five decimal places. So 20 plus 0.81666 plus 0.01138. Yeah. So I get approximately 20.82804 degrees. If all of this is confusing you, just what you need to do is basically go back and review conversions. And I can help you with that during my office hours, or you can go to the tutoring lab and just tell them, hey, I'm having trouble doing conversions, and they should be able to help you. Any questions? I'm about to go type this into the computer and see what it does. Okay, round to the nearest second is needed. Wait a minute, I'm looking at the wrong one. Okay, do not round until the final answer, then round 2 decimal places. See, the instructions told us 2 decimal places. So we had, so what do you think, 20.828? We're going to round to the second decimal place. We're going to be looking at that 2. So we look at the number to the right of it, which is 8. It's bigger than 4. If it's a 5, 6, 7, 8, or 9, we round up. So it's going to be 20.83. And then, yeah, it already has the degree symbol, so I don't need to put that there. Okay, there we go. All right. Now, that's how you convert an angle to decimal if you're given degrees, minutes, seconds. Next thing is the other way around. So what if you're given the angle in degrees as a decimal and you want the minutes and seconds? Okay, so what we're going to do is this is going to be a little confusing, but let's just follow through it. We know that this is 25 degrees plus 0.476 degrees. Do y'all agree with that? It's 25 degrees and then you're adding 0.476 degrees. I would like to somehow convert this first to minutes. Now, the conversion we have for minutes and degrees is this. Is 1 degree was 60 minutes, or you could use 60 minutes is 1 degree. Right? Those are the 2 conversions. So I want to get rid of the degrees. So what I'm going to do is multiply this by, let's see, I'm going to call on somebody. Is Karen here?
Yes, I am.
Hey, Karen. So what should I do? What should I take? 0.476 degrees. What should I multiply that by to get rid of the degrees and create minutes?
The 60 over 1.
Yep, 60 minutes over 1 degree. So then the degrees will cancel. And now, Karen, do you have a calculator?
I don't have it with me.
No? Okay, I'll do it. It's all right. So I'm going to multiply it. All right, everyone? I'm getting here 28.56 minutes. Okay. So here's where we're at now. This line is now going to be written 25 degrees plus not 0.476 degrees. We're going to write 28.56 minutes. We're not done. We need to recognize that that means 25 degrees plus 28 minutes plus 0.56 minutes. So what I'm doing here is I'm breaking this 28.56 minutes into 2 pieces. See that? And now I'm going to take this and convert that to seconds. So that means I need to take 0.56 minutes and multiply it by, let's see, is Anna Marie here?
Yes.
Is this making sense, Anna Marie?
Yes.
Okay, so what am I going to multiply that by? Do you want me to write the conversion factors down or no?
You're going to multiply by 60 minutes over 1 second.
60 minutes over 1 second. 60 minutes over 1 second. So those were the other 2 conversions that are not on this page. Let me see, they are right here, right? So we are using this one right here, right there, 60 seconds. So did I write that? Hold on, I wrote that backwards, I apologize. 60 seconds over 1 minute. There we go. So that way the minutes will cancel and you'll have seconds appear. So the minutes are going to be gone. And so we get our calculators and we do 60 times 0.56. I get 33.6 seconds. So here's where we are now. 25 degrees plus 28 minutes plus 0.56 minutes becomes 33.6 seconds. That's what we've got. So we've got it to degrees, minutes, and seconds, but we have a decimal. Do y'all see we have a decimal on our seconds? So let's see what the instructions are saying. Any questions before I go to the homework?
Yes, sir. I have one question.
Yeah.
So I understand this all, but I just want you to maybe explain it again. Why is the reason why when we had for the minutes we had the 28.56, and the reason why we moved the 0.56 over was because we don't want a whole number, or we only want a whole number.
Yes.
Okay, so
We want to measure our minutes as a whole number. Anything that's here, that decimal, we can now use that to create the seconds from.
okay, yeah, so it's seconds basically, yeah.
Because 0.56 minutes means you don't quite have 1 full minute. So you say, okay, well, how many seconds would that be then?
Okay, so that helps us also find seconds.
Yes,
as well.
absolutely.
Okay, I get it now. Thank you.
No problem. I'm going to bring up the thing here and see if we can't get the answer in here. 25. Okay, so it says round to the nearest second. So we had our answer. Our second was 33.6. So if we're going to round to the nearest second, we've got to round that thing up to 34. Do y'all agree?
Yes.
Okay, so it should be 25, 28, 34. Let's see. 25, 28, 34. we go. That's it. Questions?
Yes, I have a question.
Uh-huh.
How do you know when to use 1/60 or 60/1?
It's all about what you're trying to get to. So let me go back to this one right here. Okay, so I was sitting here with 0.56 minutes, right? And I'm trying to get it to seconds. Do you agree?
Yes.
So here's what I know. I know that there are 60 seconds in 1 minute. Oh, 1 minute. So this is the relationship that I have that connects seconds to minutes, right? This is the relationship that I have between minutes and seconds. There are 60 seconds in 1 minute. Anytime you have a relationship like this, you can create two fractions from it. You can either put the 60 seconds over 1 minute, or you can do 1 minute over 60 seconds. So that's with any conversion factor. Now, the reason I'm going to use this one is because it has minutes on the bottom. Do you see that?
Yes.
And if this 0.56, the minutes, if you look at this like a fraction over 1, then you can see that the minutes are on top, right?
Mm-hmm.
And so if I come in with 60 seconds over 1 minute, then the minute units cancel one another out. And that's what I need. In order to go from minutes to seconds, I need the minutes to go away. Does that
Okay.
make sense or no?
Yeah, no, okay. Yeah, I see why now. That makes sense.
Yeah. If you did it the other way, right? If you did it this way, and you did the 1 minute over 60 seconds, this and this don't cancel. Do you see that?
Yeah.
And so you're going to get, you actually get like minutes squared. No, this won't work. Okay.
Okay. Thank you for explaining that.
Yeah, no problem. Does that clarify it for everyone? Good question. Thank you. Okay, we're moving along. All right, so we've gotten through quite a bit. We still have 30 minutes left and we still have a lot to do. So now we're going to talk about radians. And radians are where things start to get weird for people. All right, starts to get strange here. All right, so here's what I'm gonna do to try and help you understand the radians. Put some grid up here. I'm gonna put our XY axes here. All right, now I'm gonna put a circle in here, just an arbitrary circle. See how this goes. I hate that this thing doesn't let me draw circles right in the middle. All right. Okay, close enough. Okay, that's a circle, right? Now I'm going to draw a different circle. Let me change the color of this so that we can talk about them. Make that one red. Okay, I'm going to draw another circle. Make it a little bigger. And let's make this one. I'm trying to draw it pretty precisely, and you'll see why in a moment. Make that one black. Okay, so I have a red circle and I have a black circle, okay? Now, with circles, we have the idea of a radius. We talked about that already when we talked about circles, right? So let's talk about the red circle. If I were to draw from the center to the edge along the x-axis, this right here would be the radius. Everyone agree? That little arrow represents the radius. Now, imagine, and this is so much easier to do when I'm in person in class. Imagine that I could like reach down on this paper and pick up that radius like a little string. I don't have a string. Oh, here, I have this. So imagine that, you know, I have this little string here, and that's the measurement of the radius of the red circle. What I'd like to do is take that same measurement, and I'm going to highlight it in yellow. So that everyone agrees that has a certain length to it. I'm going to take that and wrap it around the circle. So I'm going to start wrapping it around the edge of the circle. And so I'm going to wrap it around like this until it stops. And you know what? I'm going to do a different color. This is green. Okay. That's the radius of the red circle, is that green piece. but I've wrapped that around the edge of the circle until it stopped. Understand? So that if you were to walk along here from here to here, if you were to walk, it would be the same distance as walking along that edge. And then you'd have to stop somewhere, right? Any questions? Now imagine that we connect this dot to this dot. So now we've created an angle. Does everyone see the angle in here? Right there, that little positive angle? Okay. Let's just put that on the back burner. Now what I'd like to do is talk about the black circle. Now I'm going to do the same thing. So if I start at the beginning, the origin, and I walk out to the edge of the black circle, that will be the radius of the black circle. So that has a distance, right? Whatever that distance is, I can measure it. Now walk along the circle, the black circle, that same distance. And then draw the dotted line that goes out to it. And guess what? The angle that's formed is the same as this purple angle. It's the same angle. And it does not matter what size circle you use. So if I do a bigger circle, close enough. Well, get a little better. Okay, if I do a bigger circle and I start at the center and I walk out to the edge and I measure that distance and then I walk along the circle that same distance, then I guarantee you that the angle that I'll form when I connect that will be the same as it was for the smaller circle. And that is a property of circles. So this is so difficult to explain because it's so weird. When we first started talking about angles, we said, hey, someone decided to break it into 360 degrees. And we're like, well, why 360? You could have used any number, right? 100, you could have used 1,000. Someone decided 360. Later on, as we became more intelligent, we understood this, that there's this very special property that for any circle, if you take the radius and then walk along the edge of the circle, that same length of the radius, the angle that forms here is going to be the same regardless of the size of the circle. So what it created for us is a standard angle, like an angle that we could all, that you could always create, that everyone, it would be consistent. So we gave this angle a name, okay? This angle right here, we just gave it a special name. We called it 1 radian. So 1 radian, the definition is really nasty. I'm going to give it to you. I'm going to give you the definition just so you can see it. Oh, no, wrong.
It's 57.296 degrees.
Yeah, there's a way to get from radians to degrees also, but we'll talk about that in a second. I just want everyone to see this in the textbook, the formal definition that they use. Chapter
It's 180 over pi, right?
That's right. Mm-hmm. Yeah, but the question then is what's pi, right? So like, where does pi come from? So I'll get to that. Should be right here. Okay, so radian. See if they actually write the formal definition. Radian, central angle. Yeah, so I don't know if you can see this. I'm just going to read through. It's not important that we write it down. Radian measure. A central angle is a positive angle whose vertex is at the center of the circle. The rays of the central angle sub 10 intersect an arc on the circle. If the radius of the circle is r, and the length of the arc subtended by the central angle is also r, then the measure of the angle is 1 radian. That's basically them saying what I'm trying to tell you right now, which is, and I'll start from scratch. If you take any circle measure its radius, and then subtend an arc. That's the terminology. You subtend an arc along the circle that has the same length of that radius. Then the angle formed right here is 1 radian for any circle you ever draw. Okay, so that's the formal definition. So that's it. Whatever that measurement is, that's 1 radian. Would you all agree that 1 radian appears to be much bigger than 1 degree? The question, though, is how many radians are in a full revolution? So how many radians would you need? Do you all agree that that looks like about 2 radians, like from here to here? The question is, how many radians do you need for 1 full revolution? So the question is, how many radians do you need for 1 revolution? We know that you need 360 degrees to go all the way around. How many radians do you need, though, to go all the way around? I heard someone say it.
Pi radians is 180 degrees, so it would be 2 pi radians.
2 pi. So this is the first time that we're seeing this, all right? 2 pi radians equals 1 revolution. Okay, but this isn't fair, okay? Because what the heck is 2 pi? Well, what's pi, right? What's pi? I mean, we've all seen it, we've used it, but what is pi?
Pi is 180 degrees.
Yes, but what is pi? Just forget we're talking about anything else, circles, angles. Just if I walked in today and I said, hey, everyone, what's pi?
3.14.
It's a number, right? Okay, pi is a number, but I want everyone to understand that. Pi is just a number, all right? But it's a very special number. It's not just any number, it's a very special number. It is what we call an irrational number. Does anyone know what that means for a number to be irrational? It doesn't listen to you, talks back to you? No? What is an irrational number? Anyone know? It's okay.
Well,
I'll tell you, pi is approximately 3.1418. Does anyone know about this decimal? What happens if I keep going?
It goes on forever.
It goes on forever. I agree with that. So this is a what we call a non-terminating decimal. Now, that's not enough, though. To be irrational, okay, to be irrational, an irrational number, I agree, your decimal cannot terminate. It has to go on forever. But you know what? 0.333 forever doesn't terminate, right? 0.33333. But that's not an irrational number. So there's another condition that you need for it to be irrational. So it goes on forever. What? Go ahead, Maddie.
It doesn't repeat.
It doesn't repeat. It's non-repeating. That's what makes a number irrational, is that when you write it out, it has a decimal that never stops, and there is no pattern to the repetition of numbers. It's always changing. So like when you take the number, when you take the fraction 1/3 and write it out, it's 0.333 forever. This is not irrational because even though it never stops, it is non-terminating, it does repeat. And so this is not irrational. So it turns out there's an easy way to remember this. The way that you can tell a number is irrational is whether or not you can write it as a fraction. That's what irrational, rational means ratio, ratio means fraction. So all fractions, if anybody gives me any fraction, 1/3, 1/5, 4/77, 5/91. I don't care what it is. If it's a rational number, an integer over an integer, it's guaranteed that it's either going to stop repeating. It's either going to repeat, the decimal's either going to repeat forever, or it's going to terminate. In order to be irrational means you cannot write it as a fraction. And that's something that a lot of people don't know. I'm going off topic here a little bit, but that's just the way it's going to be, okay? We had this conversation, Austin, or was it Joshua? Who was it? Someone was in this conversation when I asked what number was right next to 1. Did we talk about that or no? We didn't talk about it. Okay, we're not talking about it. So we are off topic, but I want you to consider this. Think of all the numbers between 0 and 1, okay? Think of all the numbers in there. There's a lot of numbers in there, right? Would you agree? Infinitely many numbers? You think there's an infinite number of numbers in there?
Yes.
Yeah, okay. So, I mean, you could just start listing out like 1/2 is in here, 1/3 is in here, 1/4 is in here, 1/5, 1/6, 1/7. So there's an infinite number. You go forever. But my question is, if you were to just like close your eyes and just reach in there and grab one of the numbers. Okay, so you just close your eyes and grab one. So I'm just going to grab one. Here it is. Boom. And you look at it. What do you think? Do you think that there's a fraction, like something over something, that would create that number? In other words, I'm asking you, do you think that the number you pick is going to be a fraction?
Most likely it could be, yeah.
Most likely, okay. Do you think that every number in there has to be like a fraction?
No.
No, you're gonna run into something that's gonna be expressed. It has to be expressed as something else.
Yeah, so there are going to be a mixture of fractions and non-fractions in here. Okay, there's going to be a mixture. So there are rational numbers in here and there are irrational numbers in here. But the big misconception that most students come into pre-cal and calculus with is that there are so many fractions in here and so few irrational numbers. And that's wrong. So I have this is the part that's going to blow your mind, or you're not going to care. If I close my eyes and I reach in here and grab a number and I place it down in front of us and we look at it, the probability that it's a fraction, the probability, probability is like flipping a coin, like talk about probabilities, flip a coin, heads, tails, 50-50. If I close my eyes and reach in here, grab a number, look at it, the probability that it's a fraction is 0. 0. That should bother you. That should bother your brain. Because what I'm telling you is that there are an infinite number of fractions in here, right? I told you that, we all agreed there's an infinite number of fractions in here. But I'm telling you, if you randomly pick a number out of that number line, the probability that it's a fraction is 0. Which means that there's an infinite number of irrationals in there too. So there's an infinite number of both. So maybe you should be thinking, well, then it should be 50-50, right? 50-50? Well, it turns out it's not, because there's actually 2 types of infinity. We have 2 types of infinity. Now, I'm not going to get into this because I could keep talking forever about this. I want to go back to this very simple statement that took me off on this tangent here, that 2 pi radians is 1 revolution. And the reason I went off on a tangent is because I want everyone to understand, like at the end of the day, yes, you just need to know that 2 pi radians is 1 revolution. But pi is just a number, but it's a very special number, and it's weird that it shows up here, but it is. So on our calculators, what I'd like to do is I'd like to do 2 times pi, but I'm going to do 2 times 3.1418, which is about 6.28. So we're really saying here that there's about 6.28 radians in 1 revolution. And that kind of sucks for us, because 360 degrees in 1 revolution is a nice whole number, right? 360. But radian wise, there's about 6, almost 7 of these in here. So there's 1 of these, there's 2 of these, there's another one over here. That gives you 3 of them. And then there's 4 of them, and then 5. And then I'm not drawing very good, 6, and then not quite 7, we have about 6.28. So it takes about 6.28 radians to go all the way around. We will just say 2 pi radians in a full revolution. All right. Sorry, I kind of went off there, but I want to draw one final conclusion from this. So there are 2 ways there are two ways we measure angles. Degrees, and that's 360 in 1 revolution, or we can use radians, which tells us there's 2 pi radians in 1 revolution. So there's 2 ways we can measure angles. From here on out, we can either be talking about an angle in degrees or in radians. Now, when I'm talking about degrees, you will see me use a degree symbol. You'll see degrees. That tells you I'm talking about degrees. However, if I'm using radians, there is no symbol. This is important for later. We do not have a symbol for radians. I've been writing rad down for radians, but I want you to know that if somebody gives you a number and they do not put the degree symbol next to it, then you must assume it's a radian. Okay? So if I write this down, hey, show me that angle, 90. Do not show me a right angle, because I didn't say 90 degrees. I said 90, and 90 means 90 radians. Does that make sense? All right. And just so you know, as you move on in your mathematical career here, you take calculus and Cal 2 and stuff, we almost never use degrees. It's almost exclusively radians, all right? So if you're one of those people who really likes the degrees because it's 360 and 90 and 180 and 270 and like you love that, like we are gonna have to start to wean ourselves away from it because this is almost exclusively used in engineering and math. Anytime we have something in degrees, we wind up converting it into radians. So that leads to the next topic. How do we convert back and forth? Okay, let me go here. 1 radian. Arc length on unit circle. Okay, I got that. Okay, converting the degrees to radians and radians to degrees. So converting degrees to radians, and then also how do we go from radians to degrees? And the great thing about this is that there's a nice little quick formula for this. And it all comes from this idea. Don't write this down, but I said this, 2 pi radians is 1 full revolution. Do y'all agree? So if that's 1 full revolution, that's the same as 360 degrees. That's a relationship we have, right? So now if you divide both sides of this by 2, do you agree that we have this? That one you can write down. If 2 pi radians is 360 degrees, then pi radians is 180 degrees. Notice I'm not writing radians, right? Again, I'm not writing it, which means it's there. Pi radians is 180 degrees. Now, from that, I can create 2 conversion factors, either pi over 180 degrees, or I could do it the other way, 180 over pi. These are my 2 conversion factors. So those are the things that I can use to convert. What do you say we go and do the homework? You want to do the homework? That way it'll, let's look at, I think I have some conversions here to do. Right, yeah, let's do this one. We're going to convert negative 85 degrees into radians, right? Into radians. Now, when I do this, I need to get rid of degrees and turn it into radians. So if I go back and I look at my conversions, this first conversion has radians on top, degrees on the bottom. The second one has degrees on top, radians on the bottom. Which one do I want to use? The one on the left or on the right?
Left.
Left, because degrees are on the bottom, right? And it'll cancel out the degrees that we have. So I'm going to multiply this by the one that had degrees on the bottom, 180 degrees, and then pi on top. The degrees will cancel. And what we'll be left with is negative 85 pi over 180. And so we have to do this on our calculators. You have to do negative. Now, some of y'all have a pi key on your calculator. Feel free to use that. If you don't have pi, just use 3.1415, just approximate it. Mine has a pi key, so that's what I'm gonna do. So I'm getting approximately negative 1.48352. Okay, it says to round 2 decimal places. Y'all see that? So it's just negative 1.48. And this is radians, right? So I'm not going to put any symbols, so I'm ready to type this in. Negative just meant that it's a clockwise angle, right? Not counterclockwise. The negative means it's just clockwise. That's all that's important there. So negative 1.48. Okay, let me see what the next one. Now, this one says convert this angle in radians to degrees. So see how they just wrote 7 here? They didn't put degrees next to it. That means you need to know it's radians. So what would 7 radians be in degrees? So again, we're going to multiply this by something, but we got to use our conversion factor. We want to get rid of radians.
Should be 180 degrees over pi.
180 over pi. So even though there's not radians down here, we're going to use this one, 180 over pi. So we're going to go multiply by 180 degrees over pi radians. So this is the same as 7 times 180 degrees over pi. And you just use 3.14. Now it's weird because it's not here, but there's actually like a radians here and a radians down here that actually cancel. But since they're not written, you just have to understand that that's what's happening. So 7 times 180 divided by 3.1415. I'm getting about 400. It's about 401. They want rounded 2 decimal places. 0.08 degrees, because I've converted radians to degrees. So 7 radians is about 401.08 degrees. Oh, what happened?
I got 401.07 degrees.
Me too.
You know what? It didn't, my pi, I rounded pi too much. It didn't take it. Okay, well, how far do they want you to go with pi then? I guess you're going to have to use your pi key. Yeah, because that made a difference. All right, well, you know what? See how that goes. If you're not able to get that in your calculator, let me know, because it looks like they want some pretty good precision here. So make sure your calculator has the pi key. If it doesn't, approximate pi further out than 3.1415. Maybe we should all agree on how far. Just use pi. What do you want to go? How far do you want to go? Probably, let's see, maybe 5 digits would have worked. Let me just try it real quick. Okay, so 5 digits would have worked. So let's just say if you don't have a pi key, you should probably go out 6 digits, something like that, just to be safe. Okay, we don't have enough time to start the next topic, so we're going to be a little bit behind here, and there's some problems on your homework you won't be able to do. What? So let me tell you how far to go on the homework. Yeah, so you'll have to stop at problem 13. Okay, so only go up through 13. We'll do the rest next class. All right, so even, I think the assignment is due on Wednesday before
It's-
class.
It's due on the 2nd at midnight.
Yeah, so just do the first 13 problems and submit it. I know that it's going to count some problems wrong, but don't worry. Just submit the first 13 and then I'll extend it after everyone has submitted it.
Okay, so just do 1 through 13.
1 through 13, yeah.
Yes, sir.
So what we still need to do is we need to talk about, these are like applications that we need to do. And these are really going to be important later. So I don't want to rush through it here at the end. I'd rather start fresh on Wednesday and come in here and make sure everyone understands, especially the linear and angular speed. And well, all these, field width, all of these are important. So I took my time today to hopefully, you know, that it would, like, again, this is the basis for everything. So if you're having trouble, like, with the idea of any of this, it's going to cause problems later. So hopefully today went okay and homework will go okay. Any questions? Okay.
You said to submit the homework after question.